every single moment, really, we're faced with this fundamental uncertainty, aren't we? It's the question that drives everything, I think. What happens tomorrow?
Uh-huh.
Yeah.
We spend so much time dreaming, planning, worrying about what's next, trying to predict it, maybe even control it.
Yeah, hoping we can somehow dodge the the difficult stuff ahead.
It's fundamentally human, that desire.
Yeah.
But, despite all our plans, all our hopes, there's that one absolute certainty we just can't escape. Death.
Right. The ultimate end of our own personal story. And it's not just personal, is it? The way our physical selves end is tied into the whole cosmic picture.
Exactly. Whether it's the sun engulfing Earth billions of years from now or something much sooner, our physical structure, the thing that is us, it eventually dissolves.
Dissolves. Back into what?
Back into the fundamental components. Our bodies biologically cease to exist. But the atoms, the trillions of particles that made us up, they don't just disappear.
Okay.
They transition. They get scattered, basically. Blown across the cosmos, cycling through space and time.
So, okay, let's zoom out then. Our atoms become what? Cosmic dust. But does our end mean the end of everything? Does the universe even notice?
That's the fascinating contrast, isn't it? Our fate is finite. Definitely finite. But the universe, it just keeps going. It seems functionally infinite from our perspective.
So while we're becoming dust,
Stars are still being born, planets are forming in distant nebulae, seasons are changing on worlds we'll never even know exist. The universe keeps expanding, accelerating, even completely indifferent to our little transition.
and that dust, our atoms, they could theoretically become part of new stars, new planets, maybe even new life somewhere down the line.
It's entirely possible. It forces you to see the cosmos not just as empty space, but as this vast cycle of creation and dissolution. Our brief existence feeds back into that infinite process.
That perspective, the finite self against the infinite cosmos, that feels like the perfect starting point for this deep dive. We're looking at our place, our future, the sheer scale of it all.
Exactly. And we have to grapple with the big mysteries, starting with maybe the most fundamental visual one. Why is the night sky dark? Olber's paradox.
Ah, yes. If the universe is full of stars, shouldn't it be blindingly bright?
It seems logical, right? Kepler first brought it up way back in 1610. Olber's made it famous later. The paradox really stems from the old model, the steady-state theory.
Which assumed the universe was what? Infinite in size, infinitely old, and stars were just sort of spread out evenly everywhere.
Precisely. And think about the numbers involved. Our galaxy, the Milky Way, maybe 100 to 400 billion stars. Okay. Then the observable universe has like 100 to 200 billion galaxies.
That's an unimaginable number of stars.
Totally. So if the universe really was infinite in age and size and uniformly filled, then yeah, logically, no matter where you look, your line of sight should eventually hit a star.
And if every line of sight hits a star, the whole sky should be ablaze, as bright as looking directly at the surface of the sun, but obviously it's not.
It's dark. So why? This stumped people for centuries. The early answers stuck within that infinite eternal universe idea. They just didn't work.
Like the idea that the stars are just too far away?
Yeah, that one falls apart quickly. If the universe is infinitely old, light from even the most distant stars has had infinite time to get here. Distance doesn't matter for the total brightness.
Okay, so distance is out. What about Kepler's idea? Maybe the universe isn't infinite. Maybe the stars just stop somewhere.
That creates other problems, though. Like what's beyond that edge? And, more seriously, why wouldn't all that matter just collapse inwards under its own gravity?
Good point. Which brings us to Olber's own attempt. The dust idea.
Right. Olbers thought maybe there's just infinite amounts of dark stuff. Dust, rocks floating around, blocking the starlight.
Yeah.
Like cosmic fog.
Sounds plausible, actually. A lot of people probably still think that's it.
It does sound plausible, but there's a catch. Thermodynamics. This took a while to figure out, but basically, energy can't just be destroyed.
Ah, so if the dust absorbs starlight.
It has to re-radiate that energy. The dust particles would heat up, eventually getting so hot they'd start to glow themselves. They become black body radiators.
So instead of a sky full of starlight, you'd have a sky full of glowing hot dust. Still bright.
Exactly. The net result is the same. A uniformly bright sky. The paradox held firm. Until 1929.
Edwin Hubble.
Edwin Hubble. He was actually looking for evidence that the universe was static, maybe even collapsing. That was the thinking then. But his observations showed the opposite.
Galaxies were moving away from us, and the farther away they were, the faster they were receding.
Bingo. The universe was expanding. This wasn't just a minor correction. It was the foundation for the Big Bang theory. And that gave us the first crucial piece to solve Olber's paradox.
Which is?
The universe has a finite age. It's not infinitely old, it's about 13.8 billion years old.
And suddenly, the paradox collapses. If the universe is only 13.8 billion years old,
Then we can only see light from stars and galaxies whose light has had time to reach us within that 13.8 billion year window.
light from anything farther away just hasn't gotten here yet.
Precisely. When we look really far out, we're literally looking back in time. Far enough back, and we're seeing a time before stars even formed.
That's where the cosmic microwave background comes in, right? The CMB.
Exactly. That's the oldest light we can see, the afterglow of the Big Bang itself, from about 380,000 years after the beginning.
Okay, wait. If the CMB is the afterglow of the Big Bang, and the early universe was supposed to be incredibly hot and bright, like as bright as the sun's surface everywhere, then why isn't the CMB blinding us now? That light has reached us. Shouldn't the whole sky glow with that ancient light?
Excellent question.
Uh-huh.
And that leads to the second part of the solution, which is just as important, and maybe even weirder. You're right, the initial brightness should be overwhelming.
So why isn't it?
Because of the accelerated expansion of the universe, driven by something we call dark energy.
So space isn't just expanding, it's expanding faster and faster. So fast that distant regions are moving away faster than light.
That's the current understanding, yes.
Yeah.
And we should clarify, this doesn't break Einstein's special relativity. Objects aren't moving through space faster than light. Space itself is stretching and carrying those objects and their light along with it.
Like dots on an inflating balloon.
Kind of, yeah. Or imagine light waves traveling along a giant rubber band that's being stretched. As the band stretches, the light waves themselves get stretched out.
And stretching light waves, that means.
Extreme redshift. Longer wavelengths. Visible light, with its relatively short wavelength, gets stretched so much for the most distant sources that it shifts all the way down into the infrared, microwave, and radio parts of the spectrum. Wavelengths our eyes can't see.
So the sky is lit up by the CMB, by distant starlight. It's just that the light has been stretched beyond our visible range by the expansion of space.
In essence, yes. The darkness isn't emptiness, it's evidence. Evidence for both the finite age of the universe and its ongoing, accelerating expansion. Mind-bending stuff.
It really is. And this expansion creates something called the cosmic light horizon.
Yes. Think of it as the edge of the observable universe. Out there, space is extending so fast that light emitted from galaxies beyond that boundary can never reach us. It's being carried away faster than it can travel towards us.
So, there are whole galaxies, maybe billions of them, that we will never see, no matter how good our telescopes get.
That's the implication. They are beyond our horizon forever.
Wow. And that leads to a pretty bleak picture for the distant future, doesn't it? Something about 100 billion years from now?
It does. The model suggests that by then, the accelerated expansion will have pushed all other galaxies, except those gravitationally bound in our own local supercluster, beyond that cosmic light horizon.
They'll just vanish. From our view.
Effectively, yes.
Yes.
Imagine a civilization living then. They'd look out into space and see mostly nothing, an increasingly empty, dark void. They might have no way of knowing the universe was ever filled with trillions of stars and billions of galaxies.
You lose all that information. It makes our current era feel incredibly fortunate, like we're living in a golden age of cosmic information.
We really are. We exist in this brief window where the light from potentially 200 billion galaxies is still reaching us, even as expansion pulls thousands of stars beyond our horizon every single second. It's an abundance we shouldn't take for granted.
Which leads perfectly to the next big question, doesn't it? Given this vast information-rich universe we can currently see, are we alone in it?
The million-dollar question. Or maybe trillion-dollar question now. Einstein himself basically said, given the scale, it's almost inconceivable that life only exists here.
And that feeling seems to be growing. Polls show what, 2/3 of Americans think alien life is out there? Scientists seem optimistic too.
Very optimistic. People like Seth Shostak at the SETI Institute, they talk about a high probability of finding evidence of ETI, extraterrestrial intelligence, maybe within the next few decades. The numbers are just so vast. Even if life is incredibly rare, the sheer number of planets suggests it must have happened elsewhere.
It's easy to feel isolated looking up at the stars, but maybe that feeling of solitude is just a failure of perspective on our part.
That's a great way to put it. Think about our own bodies. We're covered in and filled with trillions of microbes, complex ecosystems living right on us, completely invisible without tools. Are we doing the same thing on a cosmic scale?
focusing only on life that looks and thinks like us, and maybe missing a whole spectrum of other possibilities.
It's possible. We might be overlooking forms of life or intelligence that we just don't recognize or haven't figured out how to detect yet. Which brings us to measurement. How do we try to categorize potential alien civilizations?
The Kardashev scale.
Exactly. Nikolai Kardashev, Soviet astrophysicist, 1964. He proposed classifying civilizations based purely on their energy consumption. How much power can they harness?
A very practical metric. Forget biology or philosophy, just look at the energy budget.
Right. It measures control over the environment. And where are we on this scale?
Still stuck at type 0, unfortunately, relying on burning old fossils, though maybe nudging towards 0.73.
Around there, yeah. Still fundamentally planetary and not even fully harnessing this planet yet. Getting to type 1 is the next big leap.
How long might that take? Assuming we don't blow ourselves up first.
Well, the optimistic projections, assuming something like a steady 3% annual increase in energy use, which is a huge assumption, environmentally maybe 100 to 200 years.
And what does a type 1 civilization look like?
Type 1 is planetary. They have mastered their home world. They can harness all the energy available on the planet: sunlight, wind, geothermal, maybe even control the weather, prevent major earthquakes or volcanoes, full management of planetary resources.
Okay, that's already pretty sci-fi. What's type 2?
Type 2 is stellar. They've moved beyond their planet and can harness the entire energy output of their host star.
How? The Dyson sphere idea.
That's the most famous concept, yeah. Not necessarily a solid shell, maybe a Dyson swarm. A huge constellation of orbiting solar collectors and habitats completely surrounding the star, capturing almost all its energy.
Powering what? Interstellar travel within their own system. Massive engineering projects?
All of the above.
Yeah.
They'd be masters of their solar system.
Wait, type 3.
Type 3 is galactic. This is where it gets truly mind-boggling. They harness the energy resources of their entire galaxy. Billions of stars.
How is that even possible? Manipulating black holes, moving stars around.
Maybe harnessing energy from the galactic core, building structures on stellar scales, perhaps vast networks of AI spanning light years. They'd be cosmic engineers, almost godlike from our perspective.
And just for completeness, type 4.
Type 4, that's often hypothesized as being able to harness the energy of multiple galaxies, or perhaps even manipulate the fabric of space-time, maybe even create universes. It's purely theoretical, obviously. Puts our little type 0 status in perspective, doesn't it?
Understatement of the century. Okay, so if these advanced types, even just type 2 or 3, are out there, how do we even begin to communicate across those vast distances? Our first attempts were pretty basic, physical messages.
The Pioneer plaques, the Voyager golden records, beautiful time capsules launched in the 70s, little messages in bottles thrown into the cosmic ocean.
With diagrams of us, maps, music, sounds of Earth. Voyager 1 is now, what, 23 billion kilometers away? Incredible feat of engineering.
Absolutely. But it highlights the insane challenge of distance. The odds of aliens just stumbling upon these tiny probes are infinitesimal.
And even if they did, getting a message back would take millennia. Thousands of years.
At least. Real-time conversation is just impossible with physical objects or even light signals over interstellar distances. Which is why the focus shifted mainly to radio waves.
SETI. Right, passive SETI. Listening for signals. What are they listening for exactly?
Primarily narrowband signals. Natural cosmic sources like stars or quasars tend to broadcast noise across a wide range of frequencies. An artificial signal, we assume, would be concentrated in a very narrow band, standing out against the background static.
And they focus on the water hole frequency range. Why there?
The water hole. It's a relatively quiet patch in the radio spectrum between the frequencies naturally emitted by hydrogen atoms, H, and hydroxyl radicals, OH and OH, water, H2O. Exactly. Water is crucial for life as we know it. The idea is that any intelligent life might recognize this chemically significant frequency range as a logical place to meet for communication, like a cosmic water cooler.
Makes sense. Now, there's also active SETI, or METI, actually sending messages out. Some people worry that's like shouting, "Here we are," into a potentially dangerous jungle.
That's been debated a lot. But the counterargument is fairly strong. It's probably too late to worry about that.
How so?
Our own radio and TV broadcasts, military radar signals, they've been leaking out into space for almost 100 years now, creating an expanding bubble of detectable noise traveling at the speed of light.
So any civilization advanced enough to be a threat, say type 2 or 3 capable of interstellar travel, could likely detect that leakage already.
That's the thinking. If there's a risk, we arguably took it decades ago. Sending deliberate messages probably doesn't add much extra danger at this point.
Let's say we do get a signal. or they get ours. The next massive hurdle is
Race.
language, right? How do you talk to something totally alien?
It's maybe the biggest hurdle of all. We're biased towards verbal or written language. But look at Earth. Cuttlefish use complex patterns of skin color. Bees use intricate dances and pheromones.
Their language isn't sound-based at all.
Right. And an alien intelligence millions of years ahead of us. They might communicate in ways we can't even conceive. Maybe directly manipulating fields or via quantum entanglement. Who knows? The context is completely missing.
When linguists decipher old human languages, they use related languages or context from artifacts. None of that applies here.
Imagine trying to explain, I don't know, the joy of hiking or how a drone works or appreciating a painting to a squirrel. The conceptual gap is just too vast, especially if we're talking Type 3 entities that might be like pure digital consciousnesses.
So where do you even start? Is there any common ground?
There might be one truly universal language.
Yeah.
Mathematics.
Oh, 2 + 2 = 4 is the same everywhere.
Presumably, yes.
Yeah.
The laws of physics, the relationships between numbers, geometry. Pi is a pi everywhere in the universe. These concepts should be universal truths.
So a message could start really simply, using binary code 0s and 1s to build up basic mathematical concepts.
That's the idea. Start with simple counting, then arithmetic, geometry, physics, building a shared foundation, a sort of cosmic Rosetta Stone, before you even attempt more complex ideas.
It's a fascinating challenge, but despite all this likelihood, all this searching, the universe seems quiet. Fermi's paradox.
Where is everybody?
The great silence. It's deeply puzzling. If life is probable and civilizations can become advanced, why haven't we seen any conclusive evidence? No megastructures, no obvious signals?
Lots of theories, but one really compelling one is the zoo hypothesis.
Yes, the zoo hypothesis. It's humbling, maybe a little unnerving.
Explain it. What's the core idea?
It suggests that very advanced civilizations, Type 2, Type 3, maybe higher, are aware of us, but they've chosen not to interfere.
Why not?
Perhaps they see us like we see animals in a nature preserve, or an uncontacted tribe in the Amazon. They might have a principle of non-interference, letting us develop naturally without the disruption contact would inevitably cause. We're the exhibit. So they're watching, but deliberately staying hidden, respecting our development, or maybe just not interested in talking to the ants.
It could be either, or both. From their perspective, interacting with a Type 0 civilization might be pointless or even unethical if it disrupts our own trajectory. The silence itself could be a deliberate policy.
Though, is non-interference itself a form of interference? By withholding potentially vital knowledge, are they shaping our future anyway?
That's a deep ethical question within the hypothesis, absolutely. But the silence hasn't been total, has it? There's that one famous blip.
The wow signal.
The wow signal, the most tantalizing, frustrating candidate for an ETI signal ever. August 15, 1977.
What happened exactly?
Jerry Heeman, a volunteer scanning radio signals at Ohio State's Big Ear Telescope, saw this printout with an incredibly strong narrow band signal. It lasted for 72 seconds, exactly the time it takes for the telescope to scan a fixed point in space as the Earth rotates.
And the signal itself was weird.
Very weird. It was hugely powerful, like 30 times stronger than the background noise. It came from the direction of Sagittarius. And its frequency was smack dab near the hydrogen line, 1420 megahertz, right in that waterhole sweet spot.
It looked exactly like the kind of artificial signal they were hoping to find.
Pretty much textbook. It was so unusual, so perfect, that Eamon famously circled the code on the printout 6EQUJ5 and just wrote "wow" in the margin.
The perfect signal,
But it never repeated. They pointed telescopes back at that spot immediately and many times over the decades since. Nothing. It was a one-time burst.
So what was it? A genuine ETI signal that just happened once? Some unknown natural phenomenon? Interference from Earth?
Nobody knows for sure. It remains a complete mystery, and it highlights the challenge.
Yeah.
We need a signal that's not just weird, but repeatable, to be sure. The search goes on.
And that search for signals, for things that seem out of place, it leads us into other cosmic mysteries, doesn't it? Things vanishing or behaving strangely, challenging even our basic physics.
Absolutely. Even things that seem simple at first glance can hold surprises.
Like that old classic, the Apollo moon landing photos? Why are there no stars in the sky? Conspiracy theorists love that one.
Oh yeah, that one comes up a lot, but the answer is actually pretty straightforward: physics and photography.
Go on.
Okay, first, all the landings were on the moon's day side. Second, the moon has no atmosphere, 0.
On Earth, the atmosphere scatters sunlight, making the sky blue and washing out the stars during the day.
Exactly. No atmosphere means the sunlight on the moon is incredibly harsh, direct, and unscattered. The lunar surface itself reflects that intense light brilliantly.
So the cameras.
The cameras had to be set with very fast shutter speeds and small apertures to correctly expose for the super bright astronauts, the lunar module, and the ground. Those settings were way too fast to pick up the faint light of distant stars against the black backdrop.
It's an issue of dynamic range. The stars were there, just too dim compared to the foreground brightness for the cameras, or even the astronauts' eyes adjusted to the glare to see them.
Precisely. Apparently, one astronaut, Alan Bean, I think, mentioned seeing stars briefly when he was in the deep shadow of the lander and his eyes adjusted. But out in the sun, nothing.
Makes sense. If you landed on the night side, though.
Oh, it would be spectacular. Pitch black, no atmosphere, no light pollution.
Yeah.
You'd see the stars like nowhere on Earth. That's why people talk about building telescopes on the moon's far side.
Okay, so that's one vanishing act explained, but some are much weirder, like the phantom planet Dagon.
In the Fomalhaut system.
Ah, Fomalhaut B, yes, that was a head-scratcher for years, about 25 light-years away. When Hubble first imaged it directly in 2004, it looked like a planet maybe 2 or 3 times Jupiter's mass.
But it was weirdly bright,
Yeah.
especially in ultraviolet light, and the star is young.
Very young, yeah, only about 400 million years old. Far too young, according to standard models, for such a massive gas giant to have formed that close to the star. And yes, it was bizarrely luminous, especially in UV. Some suggested maybe it had enormous reflective rings.
And its orbit was strange too, totally strange. It wasn't following a nice, predictable Keplerian ellipse. Its orbit seemed highly eccentric, and its speed was changing in ways that didn't make sense for a stable planet. It was moving outwards.
So a big, bright, weirdly orbiting object that shouldn't exist, and then it disappeared.
Pretty much. They lost track of it for a while, then went back through archival Hubble data around 2020, and they realized the object had just faded away. It was completely gone by 2014.
Gone, meaning it couldn't have been a solid planet.
Exactly.
Mm-hmm.
Which led to a radical new theory.
Which was?
Dagon was never a planet at all. It was most likely a vast expanding cloud of dust and debris from a colossal recent collision between 2 large asteroids or planetesimals, maybe each around 200 kilometers across.
A giant cosmic smash-up. And we happen to see the immediate aftermath.
An incredibly rare event, estimated to happen in a system like that maybe only once every 200,000 years. Hubble just got incredibly lucky catching it relatively soon after the collision.
And that explains everything. The brightness, the weird orbit, the vanishing.
It fits perfectly. The fine dust cloud would be very bright initially, reflecting starlight. The pressure from the star's light pushing on the tiny dust particles would explain the weird, eccentric outward movement, not gravity. And of course, a dust cloud would naturally dissipate over time, explaining why it faded and vanished. What they thought was a planet was actually the expanding shrapnel from a huge impact.
Incredible. A case of mistaken identity on a cosmic scale. But planets or dust clouds aren't the only things that vanish. What about that star, the luminous blue variable?
Oh, the star in galaxy PHL 293b. Yes, that's arguably even more unsettling. 75 million light years away.
What kind of star was it?
A luminous blue variable, or LBV? These are some of the most massive, unstable stars known. Giants living on the edge, prone to huge eruptions and brightness changes as they near the end of their lives.
Astronomers were watching it closely between 2001 and 2011, right?
And then they looked again with the Very Large Telescope in 2019, and poof, the star was gone. No sign of it after 2011.
Gone. How does a star that massive just disappear?
That's the multi-million-dollar question. There are 2 main theories, and both challenge our understanding of how massive stars die.
Okay, theory 1.
Theory 1 is that the star didn't truly vanish, but underwent a massive eruption, ejecting a huge amount of material that formed a thick, cold shroud of dust around it, completely blocking its light from our view. Like the dimming of Betelgeuse a few years back, but on a much, much bigger and more permanent scale. It basically choked itself in its own dust.
Plausible. What's theory 2?
Theory 2 is more radical. It suggests the star skipped the supernova stage entirely.
Skip it? But aren't stars that big supposed to explode spectacularly?
That's what we thought. But this theory proposes it underwent direct collapse. Instead of exploding, its core collapsed under gravity straight into a black hole, swallowing the rest of the star without the usual massive, bright detonation. A failed supernova.
So it just imploded silently, winked out of existence.
Yeah, essentially, yes.
Yeah.
No months-long light show, no nebula created, just gone. If that can happen, it means Our models for how these giants end their lives and how heavy elements get distributed through the universe might need significant revision. It's a major puzzle.
Wow. Vanishing planets, vanishing stars. Okay, let's bring it closer to home. What about glitches that affect our spacecraft? The Pioneer anomaly.
Yes, the Pioneers. A classic mystery that bugged engineers for decades. Pioneer 10 and 11 launched in the 70s, heading out of the solar system.
And starting in the 80s, they started slowing down unexpectedly.
Exactly. A tiny but persistent deceleration, pulling them back towards the sun. Something like 11 billionths of Earth's gravity. Sounds like nothing, right?
Pretty small.
But over years and years, it added up. They were thousands of kilometers off course from where they should have been based on gravity alone.
What did people think it was? New physics? Dark matter?
All sorts of things were proposed. Software bugs, tiny gas leaks, drag from Kuiper Belt objects, even modifications to gravity itself, challenging Einstein. It was a real head-scratcher for about 15 years. The key clue came when the deceleration stopped, right when their power sources died.
Their power, they ran on nuclear generators, right?
RTGs, radioisotope thermoelectric generators, yeah. Basically, heat from decaying plutonium generated electricity. And it turns out the solution was beautifully simple, but incredibly subtle. It was heat.
Heat? How?
It's called thermal recoil force. The RTGs produced waste heat, so did the main electronics box.
Yeah.
Crucially, both these heat sources were mounted on the spacecraft in such a way that most of the heat radiated forwards in the direction the probes were traveling. Heat is infrared radiation, which is photons. Photons carry momentum. So constantly radiating photons forward creates a tiny thrust pushing backwards, like an incredibly weak retro rocket.
Newton's third law, action and reaction.
Precisely. When they finally did the math in 2004, calculating the exact amount of heat radiating forward, the resulting tiny backward push perfectly matched the observed anomalous deceleration.
So it wasn't new physics, just heat radiating the wrong way.
Just good old classical physics that hadn't been perfectly accounted for in the original models. Very satisfying solution. But solving Pioneer didn't solve everything.
Right, because there's another anomaly, the flyby anomaly, and this one is still unexplained.
Still unexplained, yes. This is different. It's not a deceleration, it's an unexpected acceleration, a tiny speed boost that spacecraft sometimes get when they do gravitational slingshot maneuvers past Earth.
Slingshots are meant to boost speed, but this is more than expected.
Exactly. More than our current models of gravity predict. We've seen it multiple times. Galileo, on its way to Jupiter, got an extra 4 millimeters per second. Near Shoemaker got an extra 13 millimeters. Rosetta, Messenger, they showed it too.
And it only happens during Earth flybys, not Venus or Mars.
Seems to be only Earth, which is really puzzling. It suggests something specific about Earth itself or its interaction with space-time.
So what are the theories now, if it's not simple calculation errors?
Well, people have looked at everything. Subtle atmospheric drag effects, the precise non-spherical shape of Earth, tidal forces from the moon, the pressure of solar wind. But none of these seem to fully explain the observed boosts consistently.
Which leaves the more exotic stuff, related to relativity.
That's where the cutting edge is. One possibility is related to Einstein's general relativity, specifically an effect called frame dragging, or the lens-thirring effect.
Frame dragging? What's that?
The idea is that a massive rotating body, like Earth, doesn't just curve spacetime, it actually twists or drags spacetime around with it as it spins. It's a very subtle effect.
And maybe that twisting gives the spacecraft an extra little kick as they fly through it.
That's one hypothesis. That this frame dragging effect, or some other subtle relativistic effect related to Earth's rotation and gravity, isn't perfectly captured in our current models and is responsible for the tiny extra velocity.
How do we test that?
There's hope pinned on future missions, particularly one called STEP, the satellite test of the equivalence principle. It's designed to make incredibly precise measurements of gravity and space-time around Earth.
Wow, precise.
Like accurate to 1 part in 10 to the 17th power, unprecedented sensitivity. It should be able to definitively measure effects, like frame dragging at different altitudes, and hopefully nail down whether these relativistic effects are the cause of the flyby anomaly.
So we might finally solve this lingering mystery and maybe even confirm some subtle predictions of general relativity in the process.
That's the hope. It just shows, even in our own solar system, there are still fundamental physics questions hiding in plain sight.
It really brings this whole deep dive together, doesn't it? We started with our own, personal end, our finite existence.
Yeah, the dissolution of our atoms.
And we zoomed out to Olber's paradox, realizing the darkness itself tells a story of cosmic beginning and expansion. Then we consider the sheer likelihood of neighbors out there climbing the Kardashev scale.
Only to be met by the great silence, maybe explained by the zoo hypothesis, punctuated by tantalizing hints like the wow signal.
And finally, we end up back with these modern mysteries, phantom planets, vanishing stars, spacecraft glitches that remind us just how much we don't know, how much is still fundamentally puzzling.
It's an amazing time to be alive, really. We have access to so much information, such powerful tools, yet the universe constantly reminds us it's still mostly unexplored territory. It's like this giant jigsaw puzzle.
And we've maybe got some of the middle figured out, but the edges are still completely blurry.
Exactly. We solved why the sky is dark, but the silence remains. We understand stellar evolution broadly, but then stars just vanish. We can send probes across billions of kilometers, but tiny velocity changes still baffle us.
And we're lucky to be in this specific cosmic era, this window of abundance, before expansion hides most of the universe from future generations.
We absolutely are. The journey of discovery, of trying to piece together the puzzle of existence, is really just beginning. There are so many secrets left to unravel.
It makes you think, especially about that zoo hypothesis again. If there are vastly superior intelligences out there, maybe type 3 or 4, maybe ones that have even shed physical bodies for pure digital consciousness.
Yeah. Beings that could manipulate space-time, maybe?
What would be the first thing they try to communicate to us? To the ants in their cosmic zoo, what message would be fundamental enough?
That's the ultimate question, isn't it?
Would we even recognize it as a message? If it wasn't a radio signal, but maybe encoded in, I don't know, the fine-tuning of physical constants?
Huh.
Or in patterns we currently dismiss as noise or coincidence? Maybe the deepest secrets aren't hidden, just profoundly misunderstood by us right now. You know, when we look up at the night sky, it's kind of a strange feeling, isn't it?
How so?
Well, we're told the universe runs on these, like, perfect mathematical laws, physics, everything predictable.
Generally, yes. That's the foundation of our understanding. Fixed laws.
But then you actually look at it, you see the stars, the galaxies scattered everywhere. It doesn't look ordered at all. It looks, I don't know.
Chaotic. Like a beautiful mess.
Exactly. A beautiful mess. It feels like complete anarchy up there, visually speaking.
It's a fundamental tension. Absolutely.
Mm.
We can predict an orbit down to the millimeter, but the grand layout seems random.
So the big question we're diving into today is, what if that isn't random? What if the way things are arranged, or even the weird glitches we see, what if that's the message?
An overlooked cosmic signal hiding in plain sight. That's a fascinating way to frame it.
Yeah. Could it be something from some intelligence far beyond what we can imagine?
That's really the core of what we want to explore. We're going to peel back the layers on some of these cosmic mysteries, these anomalies.
We'll be using everything from old thought experiments to the latest data, trying to unlock things that have stumped us for ages.
And a good place to start, maybe the best place, is with something that seems incredibly simple, but took centuries to figure out.
Which is?
Why the night sky is dark.
Right. It sounds almost childish, doesn't it? Why is it dark at night?
It does. But Olber's paradox, as it's known, understanding this is key to understanding, well, everything. The size, the age, the fate of the universe. It all ties back to this.
And it wasn't actually Olbers who first asked it, was it? It was earlier.
Much earlier. Johannes Kepler, the famous astronomer, flagged it way back in 1610.
Okay, so set the stage. Why is a dark sky paradoxical? You have to think about the scale, right?
Exactly. The scale is mind-boggling. Our own galaxy, the Milky Way, has somewhere between, say, 100 and 400 billion stars. Just ours.
And then there are the galaxies.
Billions of them. The latest estimates put around 100 to 200 billion galaxies just in the part of the universe we can observe, each packed with stars.
Okay, so light sources everywhere.
Everywhere. Now, combine that sheer number with the cosmological thinking of Kepler's time and even Olber's time later on. They mostly believed in the steady-state theory.
Which means?
The universe was infinite in size, infinitely old, pretty much uniform everywhere, and crucially, it wasn't expanding, it was static.
Infinite, static, full of stars. I think I see the problem.
Yeah, if the universe goes on forever in every direction, and it's always been here.
Then no matter where you look, your line of sight should eventually hit a star. Like looking into a forest where the trees go on forever eventually, you just see tree trunks everywhere.
Precisely. Your line of sight must end on the surface of a star. If that's true, then the light reaching us from every single point in the sky should add up.
Making the night sky
Blindingly bright as the surface of our own sun, uniformly, everywhere you look.
But it's obviously not. It's dark. Wow. Okay, that is a paradox.
It puzzled people for a very, very long time.
So Kepler, back in 1610, what was his idea?
His solution was pretty straightforward, actually. He suggested, well, maybe the universe isn't infinite. Maybe the stars just stop. They extend out to a certain distance, and beyond that, it's just empty space. Darkness.
That seems logical. Why didn't that stick?
It solved the darkness problem, but it created a huge gravitational headache for 17th century physics.
How so?
If the universe was finite, just a big island of stars in an empty void, what stopped it all from just collapsing inwards? Pulled together by its own gravity over infinite time.
Right. The whole thing should have crunched down eventually.
Exactly. That fear of gravitational collapse made the finite universe idea really uncomfortable. So the infinite static, steady-state model kind of remained the default, even with this nagging darkness problem.
Until Olbers himself came along in the 1800s. What was his proposed fix?
Olbers suggested something that still feels intuitive to a lot of people today. Cosmic dust.
Like interstellar fog.
Kind of, yeah. He argued that if the universe is infinite and full of light, it must also be infinite and full of stuff. Dust, gas clouds, dark objects that absorb light.
So this cosmic dust blocks the light from the really distant stars, acting like a shield.
And that was the idea, like Earth's clouds blocking the sun. It sounds plausible, right?
It does, but you said earlier there's a flaw.
A fundamental one, based on thermodynamics. Sure, the dust can absorb the light energy, but it can't just hold on to it forever.
It has to heat up.
It has to heat up. And eventually, anything that heats up must radiate that energy away.
So the dust itself would start glowing.
Exactly. It would absorb the starlight, get incredibly hot over infinite time, and then re-radiate that energy. The total amount of radiation hitting Earth would still be immense. The sky would still be bright, maybe just glowing from hot dust instead of directly from stars.
Okay, so dust doesn't work either. The paradox holds. How long did it take to really solve it?
Almost 300 years after Kepler. It needed a complete revolution in how we saw the cosmos.
Edwin Hubble, 1929.
That's the one. Hubble's discovery that galaxies aren't static, they're moving away from us. The universe is expanding. That changed everything.
And that expansion, combined with the idea of the Big Bang, finally gave us the answer.
Two key parts, really. First, the universe isn't infinitely old. It has a finite age.
Let's break that down. The finite age theory.
Current estimates put the age of the universe at about 13.8 billion years. That number sets a hard limit.
A limit on how far we can see, because light takes time to travel.
Precisely. Light travels fast, but not infinitely fast. When we look at the most distant objects, we're looking back in time. The light from the absolute farthest reaches simply hasn't had the 13.8 billion years needed to get here yet.
And even more than that.
We're looking back to a time before stars even existed in large numbers. The very early universe hadn't formed stars and galaxies yet. It was, for a time, starless.
So we're looking back towards a dark beginning, in a way.
The furthest light we can detect is actually the afterglow of the Big Bang itself, the cosmic microwave background, the CMB.
But wait, that early universe, after it cooled enough for light to travel, wasn't it supposed to be incredibly hot and bright? The CMB comes from that era, right?
It was intensely hot, yes, a plasma glow.
So why doesn't that ancient light fill the sky and make it bright now?
And that brings us to the second, arguably more important piece of the puzzle, cosmic expansion and redshift.
The universe isn't just expanding, it's accelerating. Dark energy pushing everything apart faster and faster.
Right. And we measure this expansion rate with the Hubble constant.
Which tells us how fast things are moving away based on their distance.
Exactly. It's about 73.3 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light years. So for every 3.26 million light years further away an object is, it appears to recede from us 73.3 kilometers per second faster.
That stretching of space itself does something fundamental to the light traveling through it.
It stretches the light waves. Think of a wave drawn on a rubber band, and then you stretch the band. The wave gets longer.
This is redshift, light moving towards the red end of the spectrum, which has longer wavelengths.
Precisely. And for the most distant objects, the ones receding from us incredibly fast due to billions of years of expansion, that stretching is extreme.
So extreme that visible light
Gets stretched right past red into infrared, microwaves, even radio waves, wavelengths our eyes simply cannot detect.
So the energy from that bright early universe, the CMB, is still here, all around us.
It is. But it's been redshifted by expansion over 13.8 billion years, into low-energy microwaves, invisible to us without special telescopes.
Wow. So the darkness isn't emptiness. It's a record of the universe's age and its expansion. The light is there to stretch beyond visibility.
That's the solution to Olber's paradox. Finite age means light hasn't arrived from everywhere yet, and expansion redshifts the most distant light out of the visible spectrum.
It's kind of profound and slightly chilling when you think about the future implications you mentioned.
It is. If the expansion keeps accelerating, driven by dark energy,
Then eventually, even the galaxies we can see now will be pushed away so fast.
so their light will be redshifted beyond detection. They will cross the cosmic light horizon. Their light will never reach our descendants.
How far in the future were we talking?
Estimates suggest around 100 billion years from now. Any civilization living then, perhaps in our own merged Milky Way Andromeda galaxy, would look up,
And see almost nothing, just local stars.
pretty much, an empty, dark void beyond their local group. They'd have no direct evidence of the billions of other galaxies we see today. No evidence of the Big Bang's expansion imprinted on distant light.
It makes you appreciate being alive now. Cosmically speaking, we're in the sweet spot of information.
We really are. This era, with the CMB still detectable and distant galaxies still visible, might be relatively brief in the grand scheme of cosmic history. Every dark night sky is a temporary gift.
Speaking of dark skies, let's quickly tackle that other related question people always ask. The moon photos.
Ah, yes, the why are there no stars in the Apollo pictures
Yeah.
question.
Right. If the moon has no atmosphere, shouldn't the stars be incredibly bright and clear in those photos? Like the one of Gene Cernan saluting the flag?
It's a common misconception, often used to fuel conspiracy theories, but the answer is quite simple photography, really.
It comes down to the exposure settings.
Exactly. First, remember when the landings happened? They were all during the lunar daytime.
So the sun was out.
And on the moon, with no atmosphere to scatter the sunlight like it does here, creating our blue sky, the sun is just intensely bright. And the light reflecting off the bright gray lunar surface is also incredibly intense.
Okay, so very bright foreground. The astronaut, the lander, the lunar surface.
Extremely bright. Now think about taking a photo. You have to set the camera's exposure to capture that bright foreground properly. If you exposed it long enough to capture the faint light of distant stars.
The astronaut and the surface would be completely washed out, totally overexposed white blobs.
Precisely. The camera settings needed for the brightly lit subjects meant the exposure time was far too short to register the faint starlight in the background.
It's like trying to photograph stars from Earth next to a brightly lit stadium. You won't see them.
Same principle.
Okay.
And we actually have astronaut accounts confirming this. One astronaut mentioned that when he stepped into the shadow of the lunar module, completely shielded from the direct sun and surface glare, and lifted his heavily filtered visor,
He could see them.
he reported seeing the brightest stars and planets clearly, once his eyes adjusted to the deep black.
So the stars were there, just outshone, which actually leads perfectly into the next idea, using that perfect darkness.
Right. The lack of atmosphere and the potential for true darkness makes the far side of the moon, the night side, an ideal place for future telescopes, which connects neatly to our search for other things out there, cosmic messages.
Yeah, moving from understanding the background darkness to searching for signals within it. Given everything we've just discussed, the age, the size, the number of stars and galaxies.
The probability of life existing elsewhere seems incredibly high, doesn't it? Mathematically, it feels almost inevitable. Einstein certainly thought so.
He said something like, life elsewhere, without a doubt, does exist.
That's the quote, yeah. Strong words from him.
And it seems like the public largely agrees now. You mentioned that Pew Research poll.
It's quite striking. Something like 2/3 of Americans believe alien life is out there. And maybe more surprisingly, over half trust military reports about UFOs or UAPs as potential evidence of intelligent life.
That's a big shift. And scientists in the field, like at SETI, are optimistic too.
Very. Seth Shostak at the SETI Institute has been quite bullish, predicting we might find tangible, undeniable evidence of intelligent extraterrestrial life within just the next couple of decades.
Wow. Okay, but intelligent life could mean a huge range of things, right? Not necessarily little green men in flying saucers.
Absolutely. The spectrum is potentially vast. We could find microbes, simple organisms detected through biosignatures in an exoplanet's atmosphere. That would be huge.
Or we could find something way, way beyond us.
Exactly. Civilizations potentially millions or billions of years older than us.
Yeah.
Their capabilities might seem like magic, or even godlike, manipulating energy and matter in ways we can't conceive.
Which is where the Kardashev scale comes in handy, right? To try and categorize these potential super civilizations.
It's a useful framework, proposed by Nikolai Kardashev back in 1964. It classifies civilizations based purely on the amount of energy they can harness.
Okay, so type 1.
Type 1 is a planetary civilization. They've mastered the energy resources of their entire home planet. Controlling the weather, maybe tapping geothermal energy on a massive scale. Fusion power. Planetary unity, essentially.
And where are we on that scale? Still struggling with climate change and basic energy needs?
We're estimated to be around maybe 0.73 right now. Still a type 0 civilization, technically. Some physicists estimate if we keep increasing our energy use by, say, 3% a year, we might hit type 1 in 100 to 200 years.
Yeah, then type 2.
Type 2 is the stellar civilization. They've moved beyond their planet and can harness the entire energy output of their host star.
This is the Dyson sphere idea. Building structures around a star to capture all its energy.
Exactly. Dyson spheres, or maybe more realistically, Dyson swarms vast clouds of orbiting collectors. Finding the weird infrared signature of such a megastructure blocking starlight is a key thing SETI looks for. A technosignature.
And type 3.
Galactic civilization. Harnessing the energy of an entire galaxy. We're talking about manipulating stars, maybe feeding black holes, potentially fiddling with space-time itself for travel or communication. Truly staggering capabilities.
And there's even talk of a type 4.
Theoretical, yes.
Right.
A civilization that could harness the energy of the entire universe, or perhaps even create universes. It bends the mind.
So given we're barely a type 0.73, our first attempts to communicate outwards were pretty basic, right? Physical messages.
Very basic, yeah. We essentially threw messages in bottles into the cosmic ocean. The Pioneer plaques and the Voyager golden records.
The Pioneer plaques had those iconic line drawings, the man and woman, the map of our solar system.
And a pulsar map, meant to triangulate our position based on the regular pulses of neutron stars. A sort of cosmic address, designed by Carl Sagan and Frank Drake.
And the Voyager records were even more ambitious, actual records sent out on the Voyager probes.
Gold-plated copper records, yeah. A committee led by Sagan put together this incredible time capsule, 115 images, sounds of Earth like wind, thunder, animals, music from all sorts of cultures, greetings in 55 languages.
It's a beautiful sentiment, but practically speaking, the chances of these being found?
Vanishingly small. Space is just too big. They're tiny objects drifting for potentially billions of years. Even if one happened to pass through another star system, the odds of it being detected are minuscule.
And even if found, it's one-way communication. No chance for a reply for millennia, eons.
Exactly. They're more like monuments or perhaps archives of humanity for the very distant future, rather than active communication attempts.
Which is why most modern efforts focus on signals, right? Active SETI or METI messaging extraterrestrial intelligence.
Well, METI, deliberately sending messages, is actually quite controversial. Many scientists worry about broadcasting our existence without knowing who might be listening.
The don't shout in the jungle argument.
Precisely. So most effort is passive SETI, just listening, using huge radio telescopes to scan the skies for signals that look artificial.
What kind of signals are they looking for?
Typically narrow band signals. Natural cosmic sources tend to emit radiation across a broad range of frequencies. An artificial beacon, however, could be focused into a very narrow, efficient channel. That would stand out against the background noise.
And they often look in a specific frequency range, the water hole.
That's right. It's a relatively quiet part of the radio spectrum between the natural emission frequencies of hydrogen, H, and the hydroxyl radical, OH. H and OH make water, H2O.
And since water seems crucial for life as we know it,
the thinking is that maybe other water-based life forms would choose this symbolic and quiet channel for interstellar chat. It's a logical place to listen.
But okay, let's say we do detect a clear, narrow band, artificial-looking signal. Then comes the really hard part, right?
The language barrier, arguably the biggest hurdle of all. How on Earth, or off Earth, do you decipher a message when you have absolutely zero shared context? No common language, no common culture, maybe not even common senses.
It's like trying to explain, I don't know, a movie to a dolphin or music to an ant. The concepts might not even translate.
Exactly. We think in terms of sound or radio waves, but what if an alien intelligence communicates through manipulating gravity fields or complex patterns of light like a cuttlefish or something we can't even imagine? How do we decode that?
So the fallback is often math.
Math is seen as potentially the only truly universal language. Basic concepts like 2 plus 2 are 4, prime numbers, the value of pi, the structure of atoms. These things should be true everywhere, regardless of biology.
So the idea is to send or look for messages encoded using fundamental mathematics, maybe using binary code, zeros and ones.
That's the leading hypothesis for how you might construct a universally understandable message. Start with math, build up complexity. It would be an immense intellectual puzzle, both to send and to receive and decode.
But this whole discussion, the high probability of life, the potential for super advanced civilizations, our attempts to listen at all leads back to that big, nagging question Enrico Fermi asked.
Where is everybody? The Fermi paradox, the great silence.
If the universe should be teeming with life, maybe even advanced life, why haven't we seen any definitive evidence? No signals, no probes, no giant alien constructions.
There are dozens of potential answers, some quite sobering. Maybe life is incredibly rare after all. Maybe intelligent life inevitably destroys itself. Maybe interstellar travel is just too hard.
Or maybe they're deliberately hiding from us. The zoo hypothesis.
That's one of the more intriguing ones. The idea that advanced, perhaps type 2 or 3 civilizations are aware of us but choose not to interfere.
Correct.
Maybe they see us as too primitive, like we view ants in an anthill. Why would we try to talk to the ants? Or maybe they have a strict non-interference policy, a prime directive, to let us develop naturally without contamination. We're in a cosmic zoo or wildlife preserve.
So we might be under observation, but deemed not ready for contact.
It's a plausible, if slightly unsettling, explanation for the silence. Or perhaps the silence isn't absolute. Perhaps we did receive a message just once.
The wow signal.
The ultimate anomaly in the search. August 15th, 1977.
Yes.
Jerry Emmon at Ohio State University's Big Ear Radio Telescope.
He saw the printout and just wrote wow on it, right?
He did, because the signal was, well, it was almost exactly what SETI researchers have been hoping to find for decades.
What made it so special?
Several things. First, its frequency. It was smack dab in the protected waterhole region right near the hydrogen line frequency at 420 megahertz. A very logical place for an artificial signal. Second, it was extremely narrowband, much narrower than any known natural source. Third, it was strong, really strong, peaking at about 30 times the intensity of the background cosmic noise.
And fourth, the duration.
The duration was the clincher. The Big Ear telescope was fixed. It used the Earth's rotation to scan the sky. Any point source in the sky would pass through its beam for exactly 72 seconds.
And the wow signal lasted.
Exactly 72 seconds. It rose in intensity as it entered the beam, peaked in the middle, and faded as it left, perfectly matching the profile of a fixed extraterrestrial source passing through the telescope's view.
It came from the direction of Sagittarius.
Near a star group called G Sagittarius, yes.
Yeah.
The printout showed the intensity rising and falling, represented by the sequence 6EQU JCO5. That U represented an intensity level over 30 times background noise.
So they checked everything. Earth interference, satellites, planes.
Exhaustively. They ruled out terrestrial sources, satellites, reflections off space debris. The signal had all the hallmarks of being truly extraterrestrial and artificial. But it was never detected again. Despite Amon and others trying immediately, and many other telescopes pointing at that same patch of sky over the years, nothing. Silence.
Just that one 72-second burst.
Just that once. And for SETI, repeatability is everything. A one-off event, no matter how compelling, remains an anomaly, not proof.
Have there been any other explanations proposed? Natural ones?
People have tried. Some suggested it might have been an unusual signal reflected off the hydrogen cloud of a passing comet, but those explanations struggle to account for the extreme narrow bandwidth and the perfect 72-second duration match.
So it's still unsolved?
Officially, yes. But wow. Signal remains the most tantalizing, frustrating, and deeply unexplained potential alien message ever recorded. A cosmic anomaly of the highest order.
Okay, so from a message that appeared and vanished, let's talk about actual things, celestial objects that seem to appear and then vanish. This feels even weirder. Where do we start?
Let's start with a relatively recent and really perplexing case. The planet, or maybe not planet, Dagon, orbiting the star Fomalhaut.
Fomalhaut. That's a fairly young star, right? Close by.
Relatively, yes. 25 light years away. And young, maybe 400 million years old, about twice the mass of our sun. And back in 2004, the Hubble Space Telescope got a direct image of something orbiting it. They named it Fomalhaut B, later nicknamed Dagon.
And right away, there were problems. Things that didn't quite fit.
Oh yeah, a whole cascade of anomalies. First off, its estimated size.
How big?
Maybe 2 or even 3 times the mass of Jupiter, which is weird. Gas giants that big aren't really expected to form that quickly around such a young star, according to standard planet formation models.
Okay, anomaly 1. Too big, too soon. What else?
Anomaly 2. It's light. Young, massive planets should be hot, glowing brightly in infrared light. Dagon wasn't. It was bright and visible, even ultraviolet light, but faint in infrared. Very strange.
Anomaly 3.
Its sheer brightness in visible light. It was incredibly radiant, way brighter than expected for its infrared temperature. This led to speculation that maybe it had a huge reflective ring system, much larger than Saturn's, bouncing starlight back at us.
So big, weird light signature, possibly huge rings. What else?
Anomaly 4. Its habit. It was on a very eccentric, highly elliptical path, taken maybe 1,700 years to go around Fomalhaut. And weirdly, as they tracked it, its orbital path seemed to be, well, not quite following Kepler's laws. It seemed to be moving outward slightly.
Okay, that's a lot of weirdness for one object, so they kept watching it.
They did, using Hubble images taken over several years, from about 2004 to 2014. And they noticed something else odd. It seemed to be gradually fading, and maybe even expanding slightly in size.
Fading and expanding, that doesn't sound like a stable planet.
Not really. Then came the big shock. In 2020, astronomers went back through all the archived Hubble data, and they realized Dagon wasn't there anymore in the images taken after 2014.
It just vanished, a planet 2 or 3 times the size of Jupiter.
Poof. Gone.
Yeah.
As if it had just dissipated into nothing between 2014 and when they reanalyzed the images.
Okay, how is that even possible? Did it explode, collapse, new physics?
Exotic explanations were definitely considered. But the most plausible answer, while statistically mind-blowing, is actually simpler, if incredibly unlikely.
Which is?
Dagon was never a planet at all.
It wasn't. Then what did Hubble photograph?
It was likely a vast, expanding cloud of incredibly fine dust.
Dust. Where did the dust come from?
From a massive, catastrophic collision between two large, icy bodies, maybe planetesimals or protoplanets, each perhaps around 200 kilometers in diameter.
A giant asteroid collision, basically.
A truly giant one, yes.
Yeah.
And the timing is key. This kind of massive collision is thought to be incredibly rare in any given star system, maybe happening only once every 200,000 years or so.
So Hubble just happened to look at Fomalhaut right after this super rare collision occurred. That was coincidence number 1.
Exactly. A huge stroke of observational luck, or unluck, depending on how you see it. And that collision hypothesis suddenly explains all the weirdness.
Oh.
Well, the initial bright object wasn't planet. It was the immediate expanding debris cloud from the impact, made of tiny dust and ice particles, which reflect visible light well, but don't get hot enough to glow brightly in infrared. That explains anomaly 2 and 3.
Okay. And the size and fading.
That was coincidence number 2. We were watching the dust cloud literally expand and disperse over time. As it spread out, it got larger but fainter, just as observed between 2006 and 2014.
And the weird orbit, anomaly 4.
That was coincidence number 3. A solid planet follows predictable gravity, but a diffuse dust cloud. It's pushed around by stellar radiation pressure from Fomalhaut. It wouldn't follow a nice Keplerian orbit. It would drift outwards eccentrically, just like Dagon seemed to be doing.
So it wasn't a planet vanishing. It was a temporary dust cloud dispersing until it was too thin for Hubble to see anymore.
Precisely. By 2014, the cloud, though still perhaps hundreds of millions of kilometers across, was composed of such fine, micrometer-sized particles that it just became invisible to Hubble. A cosmic vanishing act explained by an incredibly rare event observed at just the right time.
Wow. That's almost more amazing than finding a weird planet.
But Dagon isn't the only thing that's vanished, right? There was Alpha Centauri blah.
Ah, yes, the supposed closest exoplanet, announced with great fanfare in 2012.
Found using the Doppler method, the radial velocity method, which is usually really reliable.
Extremely reliable, yeah. It detects the tiny wobble of a star caused by an orbiting planet's gravity. The claimed detection of Alpha Centauri blob just 4.5 light-years away seemed solid based on tiny velocity shifts in one of the Alpha Centauri stars. Error margin less than 0.1%.
But then it vanished too.
3 years later, a different team reanalyzed the same data much more rigorously. And they concluded the signal wasn't a planet at all.
So what was it? Another dust cloud? No. This time it seemed to be just noise. Either instrumental effects in the telescope, or maybe stellar activity on the star itself mimicking a wobble, combined with artifacts in the mathematical analysis used to pull the faint signal out.
So a phantom signal, a ghost in the machine.
Pretty much. It highlights just how hard it is to be certain when you're looking for these incredibly subtle effects at the very edge of our detection capabilities. Sometimes the anomaly is just an error.
Okay, but calculation errors are one thing. What about when an entire star disappears? That seems harder to explain away, like that luminous blue variable star.
Right, in the dwarf galaxy PHL 293b, about 75 million light-years away, this was a non-entity, a massive, unstable type of star called a luminous blue variable, or LBV.
What are LBVs known for?
They're like stellar ticking time bombs. Hugely massive, very bright, and notoriously unstable. They go through violent eruptions, shedding mass, fluctuating wildly in brightness. They're thought to be in the final stages before going supernova.
And this particular one was studied for years.
Yeah, astronomers monitored it carefully from 2001 up to 2011. They knew it was there, they knew its properties. Then in 2019, a team went to observe it again.
Yeah.
It was gone,
Yeah.
just not there. Checking archival data confirmed it had vanished sometime after 2011.
Okay, a massive, super bright star doesn't just vanish quietly. They're supposed to go out with a bang, right? A
Yeah.
huge supernova.
That's the standard picture, yes.
Yeah.
A star that massive should undergo a core collapse supernova, a type 2 supernova, which would be incredibly bright, easily detectable even at 75 million light-years, briefly outshining its entire host galaxy.
But no supernova was seen from that location between 2011 and 2019.
Nope.
Yeah.
Nothing. Which leaves two main possibilities for its disappearance.
What's the first, maybe less dramatic one?
Hypothesis one is that the star didn't actually disappear, it just dimmed dramatically and threw off a huge, thick shell of dust and gas. LBVs are known to do that.
So it basically hid itself, like putting up a giant dust curtain.
Kind of like that, yeah. If it dimmed significantly right as it ejected a dense, cold cloud, it could become invisible to our current telescopes, at least temporarily. Think of how the star Betelgeuse dimmed mysteriously a few years back, possibly due to a dust cloud.
Okay, that's plausible. What's the other, more radical hypothesis?
Hypothesis 2 is that the star underwent what's called a failed supernova. It skipped the explosion entirely.
How does that work?
The idea is that for certain massive stars, when their core collapses under gravity, instead of triggering a massive outward explosion, the collapse is so complete and rapid that the star just implodes directly into a black hole.
Without the big light show.
Exactly. The outer layers just fall inwards without the massive shock wave blowing them apart. It collapses quietly into a black hole.
If that happened here, it would mean massive stars can die without us necessarily seeing them explode.
It would. It would mean our census of supernovae might be missing a whole class of stellar deaths, and that black holes might form more commonly and more quietly than we thought. It's a fundamental challenge to our models of how the most massive stars end their lives. Another profound observational anomaly.
It's amazing. We've gone from the whole sky to distant galaxies to vanishing stars. But weird glitches happen much closer to home too, right? Even with things we bolt and launched, like the Pioneer probes.
Ah, the Pioneer anomaly, a classic. We're talking Pioneer 10 and 11, launched way back in 1972 and 1973.
The first probes to cross the asteroid belt visit Jupiter and Saturn. They carried those plaques too.
That's them.
Yep.
True pioneers. But as they flew further and further out beyond Saturn, heading towards interstellar space in the early 1980s, the mission controllers noticed something really strange in their navigation data.
Something was off with their speed or position.
Both probes were slowing down, just a tiny, tiny bit more than they should have been according to all known physics, gravity from the sun, planets, everything.
Like something was pulling them back towards the sun, an unknown force.
Exactly. It was an unexplained, persistent deceleration. Incredibly small, mind you.
How small are we talking?
About 11 billionths of Earth's surface gravity. Absolute minuscule.
But over years and vast distances.
It added up. Every year, the probes were thousands of kilometers closer to the sun, closer to Earth, than predicted by the best orbital models using general relativity.
And this went on for years.
For about 15 years, this tiny anomaly persisted, affecting both spacecraft in the same way. It baffled scientists. People started wondering, seriously wondering, if maybe Einstein's theory of gravity needed tweaking over long distances. Was this evidence for new physics?
That's a huge claim based on such a tiny effect. Why was it so hard to pin down?
Because the effect was so tiny. For years, it could be potentially explained away as tiny gas leaks from the thrusters, or errors in measuring their position using the Deep Space Network, or even solar radiation pressure miscalculations.
But eventually the evidence mounted that it was real and persistent.
Yes. By the time scientists were convinced the anomaly was real and needed explaining, The probes themselves had long since gone silent. Their power sources were dying.
So they couldn't just ask the probes what was happening.
Nope. The only way to solve it was to become data archaeologists, which is where Slava Turishev and his team at JPL came in.
They went back to the original mission data.
They launched this incredible, painstaking effort to recover all the raw telemetry data from the Pioneer missions, going back decades. We're talking finding and reading old magnetic tapes, optical discs, 43 gigabytes of vintage data from the 70s and 80s.
Like finding ancient scrolls, what did they find buried in there?
The answer wasn't new physics. It was subtle, overlooked engineering. The anomaly was caused by the spacecraft themselves. Thermal recoil pressure, heat.
The probes were giving off heat.
Yes, they had two main sources of waste heat on board. The electrical equipment in the instrument compartment, and more significantly, the radioisotope thermolytic generators, the RTGs, which use decaying plutonium to generate power.
Okay, so they generated heat. How did that slow them down?
The key was where these heat sources were located and which way the heat radiated. Most of the waste heat was radiated preferentially forward in the direction the spacecraft were traveling.
And heat radiation, infrared photons, carry momentum.
Exactly. Just like exhaust from a rocket, photons carry momentum. So by radiating heat forwards, the spacecraft were creating a tiny, but constant thrust backwards, a recoil force pushing them back towards the sun.
Like an incredibly weak retro rocket.
Perfectly put. And when Turishev's team modeled this thermal recoil force based on the recovered engineering data about the heat output and the spacecraft design.
It matched the anomalous deceleration exactly.
Perfectly. It accounted for 100% of the unexplained slowdown and the final proof. The anomaly stopped right around the time the telemetry showed the plutonium in the RTGs had decayed to the point where they weren't producing significant heat anymore.
Wow. So Einstein was safe. The anomaly was just subtle engineering physics.
A brilliant piece of detective work, confirming known physics rather than overturning it. Sometimes the simplest explanation, even if hard to find, is the right one.
But, okay, Pioneer was solved. Is that the end of spacecraft anomalies?
Not quite. While Pioneer's mystery is closed, another, arguably more puzzling anomaly persists. The flyby anomaly.
Flyby anomaly? What's this one?
This one is almost the opposite of Pioneer. Instead of an unexplained slowdown, several spacecraft have experienced an unexpected increase in speed during Earth gravity assists.
Gravity assists, that's when they swing close past a planet like Earth to get a speed boost, right? A gravitational slingshot.
Exactly. Missions like Galileo, heading to Jupiter, near Shoemaker to an asteroid, Messenger to Mercury, Rosetta to its comet. They all used Earth flybys to gain speed.
And they gained too much speed.
Sometimes, yes. A tiny, unexplained extra velocity boost over and above what standard gravitational calculations predict.
How much extra?
It varies, but the most cited example is near Shoemaker, which gained an extra 13 millimeters per second during its Earth flyby. That sounds tiny.
But over millions of kilometers to Mercury or Jupiter.
It throws off the navigation significantly. The spacecraft arrives earlier or on a slightly different trajectory than planned, and it's happened multiple times with different spacecraft, suggesting it's a real, repeatable phenomenon.
So what could be causing this, if it's not heat recoil like Pioneer?
That's the mystery. All the conventional explanations have been looked at and seem to fall short.
Like what? Atmospheric drag.
No, these flybys happen well above the main atmosphere. Leaking fuel, heat radiation. Again, calculations show those effects are too small or in the wrong direction.
What about Earth itself? It's not a perfect sphere. Its gravity field is lumpy.
That's been modeled extensively too. While Earth's uneven gravity does affect orbits, it doesn't seem to explain these sudden specific velocity kicks during the flyby geometry. If it did, satellites in Earth orbit should see similar effects constantly, and they generally don't.
So the explanations start getting more exotic.
They have to. People have explored things like the influence of tides, solar wind pressure near Earth, even subtle effects from dark matter. But the most persistent ideas involve relativity.
Like maybe Earth's rotation drags space-time around with it? Frame dragging.
That's one possibility. Maybe the way Earth's rotation twists space-time gives an extra unmodeled kick to spacecraft passing through in just the right way. Or perhaps there's some other subtle interaction with Earth's gravitational field, maybe related to the spacecraft's trajectory relative to the equator, that our current models don't fully capture.
It sounds like something that's really hard to test from existing data.
Extremely hard. Which is why there's now a push for dedicated missions to investigate it, like the proposed STEP mission.
STEP, what's that?
Satellite Test of the Equivalence Principle. It's a mission concept selected by the European Space Agency, designed to be the most sensitive gravity experiment ever flown.
Sensitive.
Aiming for precision down to 1 part in 10 to the 17th power. Just incredible accuracy.
And the idea is to fly it in orbits that mimic the flyby conditions.
Exactly. Fly it through the specific altitudes and velocity regimes where the anomalies have been seen. If the effect is gravitational, if there's some subtle deviation from standard gravity near a rotating body like Earth, STEP should be sensitive enough to measure it directly and see how it changes with distance and trajectory.
So this could finally tell us if the flyby anomaly is a hint of new gravitational physics or just some incredibly subtle conventional effect we've missed.
That's the hope. It's our best shot at resolving this lingering puzzle that keeps popping up in our most precise interplanetary navigation. #outro.
Wow, what a journey. We started just by looking up at the night sky wondering why it's dark.
And found the answer wasn't simple emptiness, but this incredible story of the universe's birth, its age, its ongoing expansion, written into the darkness itself.
Then we dove into the search for messages, for intelligence, grappling with that profound silence.
A silence perhaps broken just once by that tantalizing, still unexplained, wow, signal, a perfect candidate that just won't repeat itself.
We saw planets, or what looked like planets, literally vanish before Hubble's eyes.
Only to realize we'd likely witnessed an astonishingly rare cosmic collision, a statistical near impossibility playing out right when we happened to be looking.
And even with our own technology, our own spacecraft venturing out, we found glitches, anomalies.
The elegant solution to the Pioneer puzzle, hiding in plain sight in the engineering data, confirming known physics.
But also the persistent mystery of the flyby anomaly, that little extra kick that still defies easy explanation and keeps hinting that maybe, just maybe, our understanding of gravity isn't quite complete.
It really feels like we're just scratching the surface, doesn't it? We build these incredible models, these sophisticated theories, but the universe keeps throwing us curveballs. It's like a giant jigsaw puzzle where we only have a few edge pieces.
It makes you think, if even things we built like Pioneer and things we watched closely, like Dagon, can present these anomalies that stump us, at least initially.
Anomalies that sometimes take decades of data recovery or accepting wild statistical improbabilities to resolve.
Then what about the next unexpected signal, the next vanishing act, the next spacecraft glitch? What might that reveal?
Could the next anomaly finally point towards a truly new, fundamental law of physics? Something lurking just beyond the reach of our current understanding.
What secrets are still hiding out there waiting for us in this particular cosmic era we're lucky enough to live in?
What happens when we finally decode a real message? Or maybe, even more profound, when we realize the message was the anomaly itself all along?